Okay, everyone, we're ready to go now. If you're just coming in, try and find a seat quickly. Thanks for quieting down. Hope you're all well. Hope you had a good weekend. Okay. So, a couple of things to point out before we get started. There's a bit of a problem with the screen, so if we lose it, let me know if I don't spot it. So I'm pleased to see that really a lot of you are using the Piazza Forum already, so well done for that. 377 of you enrolled. If you haven't done so, please do so, because it's the best way that we can support you. I'm going to have to look at the screen to see what I'm doing. Okay. So, if you haven't seen this already, it's a bit small. Things are broadly organised by weeks if we tag them, and you can see them also by date as well. And you can see when you go to a question, there's an instructor. There's a question, a student answer, an instructor answer, and then there's some more comments that can go beyond that. So you can see that there's a way to contribute, both as asking questions and answering questions, and you can upload figures, and it's really quite good. So make the most of that. I really recommend it. I put a note here the other day because there's been a problem recording the live streams from the slides in the last couple of lectures. We've contacted media services to try to rectify that, so hopefully today's one will be sorted. Not sure yet about MECD, which is our Thursday lecture, but hopefully it will be recorded automatically as well. Unfortunately, all the systems are automated, so we don't get that control here. Somewhere the cameras automatically record this and send it to Blackboard, in theory. So when it doesn't work, it's not exactly clear why, but we've let them know, so hopefully that'll be resolved. What I've done, though, what I wanted to point out, because it might not be immediately obvious, is I've added some slightly edited videos from last year's first and second lectures onto Blackboard. Obviously for the benefit of people that weren't able to make those lectures last week, but please bear in mind that they were from last year. Some of the information will be a little bit out of date, and if you do watch these ones, then make sure you go through these sets of notes, which are this year's set of notes, as you do so you can spot what's different. I've tried to edit out stuff that isn't, it definitely isn't relevant anymore. Okay, so we also put a tutorial sheet. You can probably see some stuff that on there that you can't. We'll put it back to that. We put a tutorial sheet out that we're going to deliver to you on Friday. We're going to help you go through that on Friday. And I think from the comments in the forum, most of you already have had a go at that. Okay, what else have we done? There's a new book that's available to... No, this really probably isn't going to work when I do it on the desktop, but... Okay, so this is a study guide for fluid mechanics. A number of you have said, either privately to me or in the forum, that there's a number of stuff that's new, and there's some stuff that you're not that familiar with. That's kind of normal, right? That we've just introduced a whole new, if you like, discipline, a whole new topic, and the book that you have kind of virtually in front of you, the white fluid mechanics book, is a book that you're going to have probably through the 3 years of your degree in fluid mechanics. So that content is probably more than the total of the knowledge that you'll need in this area through your whole degree. So don't expect to understand it all at once. And where there are questions that we can help with, like I say, use the forum. What we've done as well, because some people find this more digestible, is we've found this study guide, which is, some of you heard of Shawm's outlines. They're basically softback, like kind of lecture note style books that cover an absolute wide range of topics, and they have a load of worked examples and practice questions, perfect for revision. You'll see that we have this here for the main topics that we're covering. I'm sure that you know, there's going to be some small differences in some of the notation, but by and large, it's going to be very similar. You know, these diagrams, we have something similar in our notes today. It's kind of core content. And this you might find more digestible. You might find it easier to follow than some of the content in the textbook. And overall, and on top of all of that, there's plenty of worked examples. At the end of each chapter, there's just lots of questions that that kind of you're guided through. So I think that you'll find that useful as well. That doesn't change the fact that this is the core text, but this is here to support as well, if you find that more digestible. Okay. So on this week, we have, again, some recommended reading from the core text, some condensed notes that, if you like, are the like 4-page summary of the core text, the main things that we're going to be covering. And I've also added, again from last year, because I thought they'd be quite useful if you struggle with some of the derivations in the text, some videos and some accompanying slides that show me talking through some of the more complicated derivations in that first few pages. So that's for you to kind of go through as and when you need it. If you understand it, you might not need to go through that, but it's there to help if you need. And so someone asked me, crikey, there's a lot of content there. Do we need to read all of this? And I mean, the answer is no. We're kind of providing you the information to support your learning. The various textbooks, you might find one more suitable than the other. You might find the videos are a better way to understand it when someone's explaining it to you than reading it yourself. And you might find the condensed notes kind of consolidate your own notes. I would recommend that you start by reading the course text, if you like, just following it through best you can. Then you go back, and some of the things that you put question marks against, you maybe look at what else is available, either via the forum or via some of the videos to support that. But you don't necessarily need to cover all of that content if you understand it as you goes. Okay. So this is the slides for today, and hopefully the video will appear here later as well. Last thing I wanted to mention is that, so we have this face-to-face online slot that I proposed would be tomorrow at 11. It seems like that's a gap. Please let me know in the forum if that doesn't work for you, but the idea here is that, it's face-to-face in inverted commas because it'll be online at the moment. Sign into the Zoom, and we'll treat it like if it was an office surgery. If you have questions, come along and by all means ask them, and I'll be around for an hour to try and help answer them. I do ask that you, if you are going to ask questions, you put your camera on so that it can be interactive. But other than that, really just feel free to ask whatever you want. And if you want to just listen in, that's also fine. Some people learn a lot from other people asking questions. Okay. That's potentially quite a lot of new information. Any questions about that? No? Good? Then we'll crack on. So, where are we? There's a question to get us started. I don't know if you can all see that, but we've got some pictures of flow around a wing here. And we've got 4 freeze frames of smoke visualization around airfoils, and then some various questions that are posted at the bottom. See people starting to answer them, that's great, about what's going on. So we're talking about pressure, mostly, today. We're talking about what does pressure mean, and how do we start to use pressure to analyze engineering problems. And so it's worth having a little bit of a think about what's going on in these flows. So, no, it's gone. So you've got these 4 pictures, and then you've got basically an aerofoil at 0 incidence, and then increasing incidence. So a very small incidence, maybe 10 degrees, maybe up to something like 40, and then maybe something like 70. And you can see quite clearly that the smoke visualization is showing you that the flow is attached, more or less. There's a bit of separation here, very large separation, and then a very deep stall here. And what I want to get you thinking about is what's going on in terms of the pressure. And if you remember what we talked about on Thursday, that pressure is basically this description for the number of particles that are hitting a surface at a certain rate, a certain space, then that should help you think about what's going on. So, who wants to give me some thoughts about what's going on in the first one? It's pretty small, so I'll try and zoom in. What can we say about points A and B? What can we say about the pressure at points A and B? Yeah? Pretty much equal. How come? Yeah, so, yeah, I mean, it's a safe bet that they're equal because it's symmetric, and yeah, you explained it pretty well. In the absence of any change, right, there's not going to be any change or difference in their behavior. So in 0 degrees, we can say pretty much that the pressure on the top and the bottom surfaces is equal. And I'm not sure what's about to come into the room, but yeah. Anyway, what does that tell us about the aerodynamics of this wing? Yeah. Okay, that's true. Yep. And any other? What about the net forces acting on this wing? 0 in all directions, up and down. Yeah. What about horizontal? I mean, close to 0, but not necessarily 0, right? Okay, so what's the next one? What can we say about C and D? What's the difference? What's changed now here? Yeah.
The pressure above C is lower than the pressure above D. That's 1. 2, there's a larger region of turbulent flow. 3, due to the wing's higher angle of attack, the wing has greater lift. The wing has greater lift.
That's correct. Yeah.
I
I think you're correct on all of those points. So, does anybody want to explain why the pressure is lower? Maybe using a molecular viewpoint. Yeah.
Is it because the empty space behind the wing creates a low pressure area for the dropping air, which means the high pressure area is sort of forced through it because the pressure molecules force through the low pressure, which then forms the material when those separate.
Okay. I think most of what you said there is right, but you've got to be careful. That there's basically a strong correlation between high velocity and low pressure. And if it's as we will come to find out in our aerodynamics and later on in this course, if the flow is going above the aerofoil faster, then that region of air is going to be at a lower pressure. But behind the aerofoil, it's potentially slowing down, it's potentially recirculating, and that's potentially going to be at a higher pressure. And that's something that comes up again, yeah.
Also, the part underneath the wing actually has the air particles can have more contact with the wing.
The air particles have more contact with the wing, yeah, because they are covering over a larger area, I suppose. Okay, right, so what about the next question, which is, what can we say about points A and C? I think we pretty much already answered that, because if C is at a lower pressure than A. So maybe a bit more interesting, E and F, and this is what we were talking a bit about just now. what's the difference in pressure between E and F, and why? Yeah, that, and how can you explain that in a... Yeah, there's a higher rate of kind of stagnate, we call it a stagnation point. So there's a higher rate of the flow kind of hitting the wall and causing a force on the wall than there is behind the wing. However, when we then look at the comparison between E and F and E and G, or just F and G, what we see is that the wing is so stalled that there's actually very little flow that's passing through that, and so there's going to be a void, if you like, of flow, a void of air, and so then there'll be a much lower pressure there, as was pointed out, in the wake than there is in the before. And that is going to lead to a net force in the horizontal direction, which is very large, which is our drag force. And actually, there's very little of that net force is directed vertically upwards, which would give you a lift force. So, although we've kind of only skated through some of the main principles of that, you can see that pressure plays a kind of a dominant role in the understanding of the flow around objects. And it's not trivial, because not only do we have to consider things like velocity when the flow is attached, but we also have to consider things like the force acting on objects and the differences in regions of flow before and after, in the wake and in the stagnation region. Okay. So, I've covered what we need to look at in terms of what we have this week. We've got some reading to do, some supporting videos, and another quiz. We're going to have 2 lectures, this one on Thursday. The tutorial, we're still working out exactly the details of that. On Friday we were told that some of it might be in person, and if that's the case, I'll get the room locations to you as soon as I have them. And I mentioned that tomorrow we'll have an online meeting, 11 till 12. Okay, so today we're going to spend some time looking at statics and understanding the relevance of the study of statics in fluid dynamics. We're going to do some of the first steps of some analysis, some mathematical analysis. Again, the mathematics is covered in the videos. If you don't capture everything that I go through today. And then we will look at some of the points on compressibility that we didn't have time to cover last Thursday, and then look at 2 last things that start to be of relevance to your engineering. So Pascal's principle and hydrostatics. Okay, statics. So statics is the situation, as it may be pretty self-evident, when you have your fluid at equilibrium. And this is when you can consider that there's no motion of fluid, there's no relative velocity of any of the fluid. The fluid as a body might be moving, but relative to adjacent packets of fluid, there is no motion. And what we will come to show that there is only a variation of pressure in this situation in the vertical direction due to gravity. There isn't one in the horizontal direction. And what we will show a bit later on in the course, we're not going to look at buoyancy until part 2, is that depending on the shape of the object and the submerged volume, there's a buoyancy vertical force acting against the pressure, the hydrostatic pressure. And we will also look at a couple of special cases. So we start off by considering a stationary fluid. We then consider a slightly more complicated case of a stationary stratified fluid, where fluids of different densities kind of stratify and form distinct layers, and we then work out how does the force vary vertically in that situation. probably either the end of Thursday or early next week, we will look at how we use hydrostatics all the time in everyday objects like manometers and barometers and hydrometers to understand local measurements of pressure. And there's an example of a manometer. And then towards the end of next week and the early of the following, we'll look at the forces on submerged objects. So like the typical case of a dam, how does the force vary along that surface? First with walls, either vertical or slanted, and then with entire submerged objects. And then we'll look at rigid body motion. So this is not a very common case, but it's a case that allows for some analysis which is relevant in engineering. And the two cases where you have a constant acceleration acting on the body of fluid. One in which it's a linear constant acceleration, as in Descartes, and another one where it is an angular acceleration, which is constant, as in the jug, which is being stirred by a centre fan or something. So we'll look at some analysis based on those two. Okay. It all starts with this. This is a discrete element of fluid, a small differential element of fluid. And this is one of two ways that we analyze fluid dynamics, differential form, where we take a very small region of the fluid and consider the forces. And in this example, we're considering a wedge. Don't worry too much why it's a wedge. It's chosen to demonstrate the principles, but it could be any shape. And we are assuming that it has certain dimensions. In this case, it's delta x in the horizontal direction, delta z in the vertical, and delta s on the slant. And we're saying in this case that there's no shear because it's a fluid at rest. That's one of the criteria of being a fluid we talked about in chapter 1 last week. There is only a variation due to the weight of the liquid in pressure, and there is no other net force on the fluid. The fluid is at rest. And so free body diagrams can apply here. And this is something that you're going to get very familiar with over the course of this degree. You isolate a region and you perform some analysis based on the overall net force. So it might be that there is in some cases there might be a net force. There might be a net acceleration acting on the fluid. But in this case, it's at rest. So the net force is 0. So we apply F equals ma, we sum all of the forces, and then we set it to 0. And pressure is a force divided by an area, so in order to get our force, we have to times it by the area. So we're going to do this. We're going to look at three things, and we're going to get three important results from this now. We're going to look first at the sum of forces in the horizontal direction, then the vertical direction, and then we're going to look at the special case where the element shrinks basically to a point. And each one of these observations will lead us to some kind of a rule that defines hydrostatic motion. Sorry, hydrostatic pressure. So first of all, summing the forces in the x direction and looking at the two pressures which are acting or have a component in the x direction. We can forget the bottom one, it's only these two. And we can say the sum of forces in the x direction is equal to the pressure px acting times delta z across the length b, and minus pn b sine theta. So this is this region here. This is the component of the slope in the x direction, and this is the pressure. And we can make a geometric substitution, as we show here. These are just our trigonometry laws. And we can substitute in to say, actually, the sine, if we want to get the x component of this force, we have to take the sine of theta times ds, and that gives us dz. And we can substitute delta z into here, and we can show that by cancelling out the b which is the width into the page, and the delta Z, we can show that these two pressures don't change. Okay? They cancel out to be 0 because there's no other net force acting on them. And this is, if you like, your first proof, your first application of elements to show that in the absence of any forces, we can show that the pressures must be equal. Okay, we do exactly the same thing now in the vertical direction. Again, we have the geometric relations, except now we're just looking at these two. So we have a component PZ acting vertically upwards, and we have the vertical down component of Pn, which is going to be cos of Pn. And we're looking at the forces with the positive vertical up notation. It's always important to define the axis so that you don't get mixed up in terms of which is positive, which is negative. You balance your forces, but this time the difference is you have an additional term due to the weight. Okay, that's the only difference between this and the last analysis. You also have a weight. And the weight is defined here. And so you can simplify this equation to be as follows. You can see immediately that various terms cancel out, and you're left with the sum of the vertical pressure and the normal pressure minus half rho g times the vertical distance are equal to 0. And this is, again, this is your first inclination, your first law explaining that the pressure in the vertical direction, Pz, is a sum of the pressure at the top of the element and the vertical height downwards in the direction of gravity. So the only thing that affects the pressure in that element is how far up or down, how large is the element in the vertical direction. Okay? Okay. And the interesting extension of those two findings is on the third slide. So we found our two results for a hydrostatic pressure. The first one is in a body of fluid at rest, the pressure in the horizontal direction is constant, and the second one is the pressure in the vertical direction is equal to the change of weight of the element. If we combine these, we can see what happens at the point when the element becomes infinitely small. You can see that these definitions are in terms of the triangle. It might not be immediately obvious, but in calculus, the triangle, capital delta, is a small but finite amount. And that means that when we reduce that term to 0, we can apply limits, calculus limits, and as we shrink that element, those dimensions tend to 0. So we see what happens in the limit, but that tends to 0. So as it shrinks, the only terms on these equations which will be affected by that shrinking is this one. And that one cancels to 0 because the delta z becomes 0. And in fact, we can drop it completely. Yeah?
Wait, what is half rho g delta z?
Half rho g delta z is coming from the previous slide.
Yeah. It's the weight of the object?
So the volume of this shape is half b, so half delta x times delta z, right? And then b is the dimension into the page. And mass, density is mass per unit volume, so mass is density times the volume. So it's the mass of the element times by g, which is the weight.
Half rho g delta z is the weight of the element.
Yeah,
So
yeah.
if the element shrinks, its weight is
As the element shrinks, it disappears. And all you have at that point is the presence, if you like, of the fluid that was surrounding where the element used to be. And that pressure is effectively, in the limit of calculus, vanishing to a point. And you can see that as Pz is equal to Pn and Px is equal to Pn, effectively what you're saying is the pressure around every side is the same. So in the limit, pressure is a point quantity. Pressure is determined by the activity of the particles in the fluid at that particular location. And so it doesn't, if you take the surfaces away, then it should have the same description. Okay? I appreciate that there's a change of pace when you're looking at mathematical forms, so it might not be immediately obvious, but please, if it wasn't clear, have another look later and convince yourself that that's the case, yeah. Is the pressure zero? Sorry? The total pressure zero. Don't worry about total pressure at the moment. Just consider pressure as a description of the activity of the particles at that point. And if you think about the particles that are hitting on the top of the slant compared to the bottom, when the wedge is of a finite size, then those activities are going to be different because one is deeper than the other. But when you reduce that wedge to an infinitely small size, then that quantity, that activity is going to be the same from any direction around that point.
Why does the element shrink? Does it shrink uniformly?
So the shrinking of the element, it's a good question, is a trick, a mathematical trick, just to see what is the nature of the term pressure. And what it tells us is that there isn't any directional dependence of pressure. Any other questions? Probably you can continue to ask them on the Piazza forum if there are, and we can pick that up later. It's an important thing to understand, but probably more important is this slide. This is the summary of what we've, if you like, understood about pressure so far. So we know that the fluid acts perpendicular to the wall. Sorry, the pressure of a fluid acts perpendicular to the wall because, like we said last week, without a surface there can't be a pressure acting on there can't be a pressure, if you like, felt by the surface, and it always acts normal to the wall. It always acts in the component normal to the wall. Other important thing that is maybe not immediately obvious, but I can help you understand it, is that as you go down a fluid, as you go deeper and deeper into a fluid, into a static fluid, then the pressure is going to increase. The force per unit area is going to increase. As anyone who's been in a swimming or in a pool or in the sea will know that the further down you go, the larger the force that you feel acting on you, and that's the same thing. It's exactly the same thing actually in the atmosphere. Although it's a much lower force, the further higher you go in the atmosphere, the lower is the pressure because there's less air above you, right? If you go to the edge of space, the force due to the atmosphere is low because basically there's nothing on top of you. Whereas here we have atmospheric pressure. We have the entire height of the atmosphere above us. So on top of that, we now know these three things. The pressure is the same on a horizontal plane. The difference is, in a constant density fluid, is proportional to the vertical distance between them. And the pressure at a point has the same magnitude in all directions. Okay. So these are our really important concepts for hydrostatics that we're going to use in the next 2 weeks, and we're going to apply them to the range of problems I showed you at the beginning. A slight detour now to cover what we didn't cover on Thursday, where we're going to talk about incompressible fluid, just for a couple of slides. Incompressible fluid, or compressibility of fluids, is something that is particularly important in aerodynamics. It's not something that we're going to be looking at all in this module, but other than these couple of slides, but it's something that you have a lot in Fluid Mechanics 2 in year 2, when you start to look at compressibility effects. And compressibility of a fluid is exactly how it sounds. It's the degree to which it can be squashed, right? If you have a bottle of water with the lid on and you try and squeeze it compared to if you have a bottle of air with the lid on, you can appreciate that it's easier to make some deformation or yield of the bottle full of air than it is full of water, because the air is more compressible. Actually, air is really quite compressible. And we can measure the compressibility of air, and we can also measure the degree to which that density changes with speed, which is probably the most important thing from an aerodynamics perspective. And most of the time, for instance, for the flow around cars, most land vehicles, we don't consider the change in the density of air, because it's so slight that actually it's not significant. It's only really at very high speed in air that, or for the analysis of acoustics, where we do need to consider the transmission of pressure waves in the fluid, which lead to noise, then we need to consider compressible effects. So, just for the purpose of completeness, because it's something that's been introduced in Chapter 1, and it's something that you're definitely going to come up against in future modules, we introduce now the Mach number, which is a ratio of a fluid velocity compared to the speed of sound in that velocity. Now, don't worry too much about what that means. It's basically saying how fast is information about that fluid transmitted through the fluid, that would be the speed of sound, compared to the speed that pocket of fluid is moving itself. In certain situations, the fluid element might adjust. It might compress or expand. But as long as the speed that it's traveling is substantially lower than that speed, then we don't need to worry about it. That's the key. And most of the time, you can consider, as long as this is less than 30%, then the incompressible approximation is absolutely fine. And we have some examples on the next slide where I was going to put this up as a discussion, but I'll talk through it because we don't have loads of time. Even with these 3 examples, you can start to appreciate the impact of a compressible flow or an incompressible assumption. A rule of thumb that you might not know is that you can basically more or less double the miles per hour to get the speed in meters per second. Sorry, half. So the 70 miles an hour is roughly 30 meters a second, and 400 miles an hour is roughly, or 380 is roughly 170. And remember that the speed of sound in air is 330 odd. So even at that very high speed, the maglev train, you've got a compressibility effect of around 50%. That's significant, but still, actually, would be reasonably accurate to assume that there wasn't any compressibility at all. It's only really when you get to transonic range of Mach numbers, 0.9 and above, where there are significant deviations from incompressible fluid dynamics. So, for all of this course, and actually most of your engineering lives, I think, it's a reasonable assumption to start at least with an approximation of incompressible flow, and then start to see what are the effects of compressibility beyond that. Of course, this is a clear example of where you can't ignore compressible effects. You have a bow shock, you have various oblique shocks and expansion waves, and this is observed by a Schlieren photo, which is sensitive to the change in density of air, so it uses the refraction of light through different air densities to show you a different shade in the picture. And next year you will be looking a lot more into this. Is there any questions before we move on compressibility? Yes?
Fluid in front of the bullet is moving faster
Than the speed of sound. Right, yeah, so the fluid in front of the bullet, or the air around the bullet, is moving so fast that there's no time for the pressure waves of the fluid to transmit upstream to account for the presence of the object. So there's an abrupt change when the flow meets the object, which results in a shock. Yep.
Are we going to learn what affects the intensity of these shock waves?
Oh, absolutely. We're not going to cover it in this module, but next year, both Mech and Aero will cover this, and in future years, Aero will take this a lot further.
Oh, it's just because of things like sonic booms we come up against this sort of stuff.
Yeah, and there's a lot of inviscid flow theory. The interesting thing about, actually, something worth pointing out now, is last week we talked about inviscid effects, and we talked about the slip condition, and we talked about the Euler equations. You can see actually, or maybe you can't, but the boundary layer effects around an object at supersonic flow are very, very minimal. So we can actually, most of the time, neglect viscosity in these cases. Viscosity is more important at low speed than at high speed. Okay. A couple more things I wanted to show you today. So this relates to, what was it, question 3 in the tutorial. I saw there was a couple of comments about it on the forum, so a number of you have managed to solve it. But probably you didn't identify that you were solving it using one of the principles of Pascal, who's obviously very closely associated with pressure, his name being used as the units, newtons per meter squared. So Pascal's principle states that pressure is transmitted undiminished in a closed static fluid. If the fluid is at constant density, and if there's no other fluids within that fluid, then you can say that the pressure at any point is simply the sum of the pressure where you start and then the change in vertical height from where you start to where you go. That's it. And we can use this principle in the domain of hydraulic forces to significantly step up the loading that we get from versus the loading that we apply. This is an example of this is given here. So you have, if you like, a system where a tube at one end has a lower diameter than the tube at the other end. It's like a piston. And you can see that the fluid is at least starting off at the same vertical height, right? So if we consider the pressure height here and the pressure height here, it's traveling down through the tube, but then it's rising again, so the pressure here and the pressure here should be equal. So we're assuming that the pressure is equal. And to a good degree of accuracy, that's the case in this situation. So if we apply a force at one side, remember, pressure is force per unit area, a force is a pressure times an area, then that pressure will be, can be used to change the force that you have by modifying the cross-section area of the other side. So let's say we have the same pressure, force by unit area for both the beginning and the end of the hydraulic lift. And if you rearrange that to make F2 the output force, the function, the subject, you have then the output force is equal to the input force times the ratio of the cross-sectional areas. And if the cross-sectional area is greater, then you'll have a larger force. If it's smaller, you'll have a lower force. And it's really as simple as that. And that's something that you will have used even in some toys like Lego. I think they even use it. And, it works. It's a really fundamental kind of demonstration of hydrostatics in action. And I think on the example that you had in tutorial question 3, it was in a horizontal situation, and you would have to consider that you're doing your analysis along the center line of the piston. Because if you deviate from the center line, then you would have a difference in vertical height. So as long as you stay on the center line, then your pressure is deemed to be constant. That's the important kind of caveat to this analysis. As long as your change in height is negligible, then this applies. And then one of the last things that I want to show you is how do we translate this into a usable mathematical form. One of the things we're going to do next is look at manometers, barometers, forces on submerged objects. So how do we translate some of the ideas that we've started to introduce into a mathematical form that we can use some analysis on? Now, we're not going to do complicated integrations in this module. The focus isn't on maths. But we need to understand how to take the question into the start of the analysis. One of the hardest things I think people find in engineering, I think, in applied engineering when you move from high school to university, it's not the maths, because probably you're all really good at maths already, but it's applying the maths. It's taking the question from an engineering sense and translating it into something that you can then solve, right? What are the assumptions that you need? What are the laws that you need to apply? And one of the things you realize very quickly in engineering is there's 1,000 different ways to solve a problem, but some of them are really quick and easy, and some of them take ages. And your job, your skill, is to find the right balance of time and accuracy. So here, we have our law that says the pressure changes only in the vertical direction due to gravity. Sometimes you see rho g written as a gamma, right? I don't know if you've seen that yet. We're going to be using that a lot in the next lecture. Rho g equals gamma, gamma being the specific gravity. And this is a way to represent the specific gravity of a fluid with one symbol, with one quantity. It's the product of the density of that particular fluid and the gravity. But for now, we're keeping it like that. And we're showing that the pressure gradient, and z is generally in the vertical up direction, so we use a standard coordinate system. So when you go down, then your pressure is increasing. So g is in the vertical down, so that's where the minus comes from. It's also sometimes confusing the convention of the coordinate system, so that's something to be aware of as well. You remember that z is usually vertically up and gravity is vertically down. So for pressure to increase going down, there needs to be a minus sign. So we can unfold, do the separation, integration by separation by parts. We have the dp, p2 minus p1 is equal to minus the integral from 1 to 2 of rho g dz. Yeah?
How do you integrate dz? Because it says p2 minus p1 is equal to minus rho g, integral to 1, then there's nothing between the integral between 1 and 2 and later in the slide.
Let me get to the end then.
Okay.
So you have here the integration between in the vertical direction of density and gravity. And what we're going to show is actually, because the density and the gravity are going to be assumed constant over this distance, then we can take them outside of the integral, okay? Because they're constant. They don't vary with distance in this analysis because we're assuming that the distance is small. Therefore, we can assume that the change in gravity, which will happen, is negligible. And the other thing is that we define our free surface, our surface of water, to be z is equal to 0. We then say that our starting pressure, P1, is atmospheric pressure. In the next lecture, we're going to introduce a gauge pressure, where atmospheric pressure is actually set to 0. And this is commonly used in a lot of measuring devices because it measures the difference between a pressure at a certain point and atmospheric pressure, which is all around us, so that's a sensible thing to do. But in this example, we're assigning P1 to be atmospheric pressure. And then we're going to integrate between 1 and 2. So we're going to be going vertically downwards. So we've got the two sides of our integral now with our definite quantities. P2 minus P1 is equal to minus rho g Z2 minus Z1. Remember, this is 1, this is 2, and this is the vertical direction of Z. So Z2 minus Z1, if Z1 is 0, this is going to be a negative number, right? Z2 is going to be negative. But if you then take into account the negative that we introduced at the beginning, because of the nature of the coordinate system, you can see that the pressure is going to increase, right? That makes sense. If it doesn't increase, then check your sign. So we have our pressure at 2 at a certain distance below the surface to be equal to the pressure that we start with, the atmospheric pressure, plus the magnitude of this distance times, so that's the vertical height, times the gravity and the density of the fluid that you've gone through. Rho GH, the hydrostatic pressure. Something you'll use 1,000 times before you're done with this degree. But that's the origin of it. And I think it does warrant another look to make sure that you fully understand the convention of the coordinate system. But in a nutshell, that's it. And that's something that we're going to be using again and again. Yes, does anyone have any questions before we finish? Yes. Yep. Let me answer this question before you make too much noise, because it's a good one. Can you stop talking, please? Thanks. So, a gentleman pointed out that we made a significant simplification by moving rho outside of the integral, right? Because we said that rho isn't a function of z. Rho does not depend on height. But in our next lecture and some of the tutorial questions that you're going to do next, rho will change on height, as it does in our atmosphere and in many cases. Like, as you go up in the atmosphere, the density is decreasing. So we need to be able to account for a rho that is changing with height. And in order to do that, we need an analytical expression that tells us how does rho change with z, how does rho change with height. If we have that, then we can integrate that. It's a little bit harder, but it's exactly the same technique. And then we can find exactly the variation with changing density height of pressure. Okay? That's it then. Thank you very much. I'll see you on Thursday. Or tomorrow, actually.